Hello and welcome back to the Code Athlete. In this video we'll have a look at the problem B of round Kickstart 2022A. It's called Challenge 9 and we'll dive right in. So Ada gives John a positive integer n. She challenges him to construct a new number without leading zeros that is a multiple of 9 by inserting exactly one digit, 0 to 9, anywhere in the given number n. It is guaranteed that n does not have any leading zeros. As John prefers smaller numbers, he wants to construct the smallest such number possible. Can you help John? So in each test case, I suppose we just get the integer n, yes. And for each test case, we output y. And that's a new number constructed without any leading zeros, and it has to be the smallest one. And the number can become quite big here, it seems. So we should perform probably string manipulation to, because this doesn't even fit in a long integer. 10 to the power of 1000. So we probably should find a solution which works on string level, because this then translates to a digit with at most 100,000 digits. A number with 100,000 digits, and 100,000 is something we can handle by the computer and not 10 to the power of 100,000. So for this you probably should know there's I don't even know how it's called in English. I knew it once. It's the sum of the digits. Let's call it just that. Sum of digits. It's this function of n. And the rule is that the sum of digits of n has to be divisible by 9, so I write it like this. And that is equivalent to 9 divides n. Let's write this the same way. So this is a divisibility operator, so 9 divides sum of the digits of n is equivalent to that 9 divides n directly. So yeah, so if we have a given n, we can compute its sum of digits quite easily by summing just the digits. And then we can compute its rest modulo 9. And let's say we get a 0, for example. Then we can choose to add, if we get a 0, we can choose to add a 0 or a 9, because both will change the sum of digits by a multiple of 9, and therefore the sum of digits still will be divisible by 9. If we have sum of digits of n, then this is the additional digit. So if the sum is 1, then we need to add an 8 such that all the digits together are again divisible by 9. For the 2, we need the 7. For the 3, we need the 6. So we see easily it's always possible. For the 9, we can again, 9 is actually not a rest modulo 9. It just goes to 8. And for the 8, we need to use 1. So only for the 0, we have the choice between two possible digits. And now we want to make the smallest number by adding this specific digit. Let's say we need to add in 6. In the case our number is something like this, and we want to add a 6 somewhere such that this adding operation gives us the smallest number. I suppose we can actually just iterate over all positions and all possibilities, which is only one possibility or two possibilities in the case of 0 here. And even if we check all, that should still be fast enough. But I mean, you could think about this a little bit more and see that actually let's make this a 7 maybe to make it more interesting. So what are the possible numbers we could get? 3, 4, 6, 7, 3, 4, 7, 6. So the smallest number would be 3,467. So like this one here. So I guess the rule to position the 6 would be to go from the front and find the first digit that's bigger than the one we need to place, and that in that position we need to insert it. But I think we can just go over all because it doesn't make really a difference. In the worst case, this is anyway the computational limit, so we just go over all positions and all possible digits, so I don't have to worry about any weird edge cases. So let's copy the sample over. And we say our digit we read is actually a string for us. And we also need to output a string because the long type can't hold enough digits for the large test cases. We compute now the sum of digits. Yes. We make a list of possibilities first. Oops. Where we will store all our constructed possibilities. Let's compute the sum of digits. Adding digits is also, it's usually just one digit, but it could be two, so we make a vector over it. And we say, okay, the first digit we could add is always, pushback here, is always, we need actually the rest. It's always 9 minus the rest. So with 9 minus the rest and the rest between 0 and 8, this is always a number between 1 and 9. And then there's the case if the rest equals to 0, then we could also have the digits 0. Because here we get with 0 as rest, we get the 9, and we want to have this case where we add the 0 and the 9. So now we have all possible digits we can add, and we have our empty vector of possibilities. So we will go over all of them. We should make a character here from this. this. Okay, here we have the character we want to add, and now we go over all positions. How many positions are there? If n is a number with 3 digits, you can see here 4 possible positions where we can put it. So yeah, we need to go with the size +1. Go over the substring from node to position. We add our current character and we add the rest of this. So set the string. Or just check if I have constructed the possibilities correctly, and we put them into our list, which we now can just sort. And we still need to have to catch the edge case where we have leading zeros, so now I guess we can just go through all possibilities. And check if the first character is bigger than a 0. And say result is equal to this possibility we found, and break our for loop. And this should work, I hope. Let's check what happens. I think we got the correct results for everything because no errors are shown in my debug output. Let's see what kind of possibilities we have. For example, for this 5, we need to add a 4, and we get the 4, 5 or 5, 4. 33, we need to add a 3. Okay, this looks all the same, not very interesting. For the 1, 2, 1, 2, 1, we need to add 6, 7, 8, 9, what? 3 plus 4, 7 is this, so we need to add a 2. And I guess this looks right here. Actually, the test cases are quite suboptimal. I want something more more diverse in numbers. So let's go with 1, 2, 3, 4. Actually, let's try the 0, 9 test case even. 1, 2, 3, 4 is a sum of digits 10, 15, or we have 18. Yes. So 18 is divisible by 9, so we can add the 0 or the 9. First it tries all the 9 positions, that works. Then it tries all the 0 positions. That looks correct here. And the smallest number is not this one. And indeed it produces a 1, 0, 2, 3, 4, 5, 4, which is indeed the second smallest number from all of these. Let me just add this to the result here. But yeah, we have, I think, a valid solution which works and is fast enough. You might wonder about the sorting of all the possibilities. Yeah, actually, let's compute the runtime here. Oh, we have memory limit exceeded. Okay, we have to look at the memory. So here MLE means memory limit exceeded. Let's first look at the runtime to see if that's fast enough. So let's say we have k digits. We know k is smaller than, what was it here? 100, yeah, it's a funny number here. Let's just say 100,000, which is 10 to the power of 5. Or let's just go for 10 to the power of 6. It's definitely smaller than that. Yes, computing the sum of digits is just linearly iterating over these chi values. So this is the runtime of k. Then generating all the possibilities, so getting this number is significantly less time than anything else. So we can just compute which add digits we have. And then the number of possibilities, again, is k plus 1. So we have a runtime for generating all the possibilities, which is k times 2 in the worst case, because we have 2 adding digits. And this is the amount of possibilities we also have. So we need to sort this list, which is 2k times ln of 2k, or log of 2k. So this is a dominating factor with respect to runtime. And then we again iterate from the front to the end of this sorted list to get the one with no leading zeros. But this is a dominating factor, and just to compute here some values, this is log of 10 to the power of 6. Log 2, of course, is something like, so log 10 to the power of 3 is roughly 10, because 2 to the power of 10 is 1024, right? So log of 10 to the power of 6 is roughly 2 times this, so it's 20. So we have here, this is roughly 20 times 2, it's 40. 40 times 10 to the power of 6. So this should still be fast enough. I'm always saying 10 to the power of 9 operations is roughly 1 second in C++ compute time. So you could say this is 0.04 seconds here for each of these test cases. And even remember these worst case test cases. So most of the numbers only have 5 digits actually. And for only 10 test cases, we have these large numbers. So the runtime is no problem. We have now the memory limit problem, and it's probably only the possibilities list, which is too big, because we store long strings multiple times. So it's basically a list of, for example, k strings. No, 2k strings even in the worst case, with each k digit. So the memory footprint is 2 times k squared. And with k being 10 to the power of 6, yeah, that's too big actually. Indeed, I can see this now. So we actually need to use this heuristic of, you know what, actually we don't need to store them all and sort them. We can just track the current best. Yeah, that's much better. Can do this, that is easy. And surely the worst case, like, I now want to just artificially create a number which surely is bigger than our optimal solution. So I add actually 2 numbers, making it much bigger, 2 9s. So I can say this is basically, I initialize it with infinity, and now I just need to find the smaller ones. Yeah, so if per cos smaller than, actually this is result, right? Just directly write this into result. Smaller than result, and per cos of 0 is larger than 0, so we have no leading zeros, then we can say result is equal to current possibility. And we don't need to put it in any list, we don't need to sort any lists, this gets even faster now. We don't have to find our solution. Yeah, it still gives the correct answers, and because we don't store the list anymore, it should have no memory limit problems. So we basically eradicated this in the memory, this k squared, so, and this 2 actually just store a number of k digits, same size as the input, and 10 to the power of 6, yeah, that's memory of characters we can handle. So that was problem B of round A 2022 Kickstart. Yeah, solved it. Again without pressure, so during competition of course I won't go into much details of this. That's why I think it's nice to have these videos going in detail through my thought process, so you can hopefully learn a bit more. But to see how I would work in competitive environment, have a look at my future videos or my past videos where I actually live streamed me solving under time pressure some of these problems. I'm looking forward to the qualification round coming up the next weekend. Join me there. So ring the bell, subscribe to the channel if you don't want to miss it. And leave a like or a comment to this video if you enjoyed it. Thanks for watching. Bye.